Let's investigate arithmetic and geometric sequences. First, let's look at arithmetic sequences. You can define arithmetic sequences using a recursive definition. So if we choose a sub n plus 1 to be the next term in the sequence, then we can take the current term in the sequence, denoted by a sub n, and we can add a common difference to this term. And that's going to get us to the next term. So n is where we are right now. That's the current term we're looking at. And to get the next term in the sequence, we just have to add this common difference. And it's called the common difference because it is the same difference between all the terms, all the neighboring terms in an arithmetic sequence. So the sequence in front and behind, they're all going to be separated by this value d. And d does not have to be positive. It can also be negative. We can use this recursive relationship to write a general relationship. I'm going to write that over here. A sub n is equal to a sub 0 plus nd. Now, I'm using a convention that differs slightly from the usual convention. Usually, people like to start numbering from 1. So they go 1, 2, 3, and so on. But in this video, I'm going to start from 0. So I'm going to use the convention that n is a non-negative integer. So it starts from 0, and it goes to 1, 2, 3, and so on. So this is the convention that I'm using. Usually, the convention is to start from 1. But I am intentionally choosing this convention because it's going to make something very clear later in the derivations that I'm going to do in this video. So the important thing to remember is this is the general relationship. So if we start from a0, that is the 0th term, the initial term in the arithmetic sequence, and we add n copies of the common difference, that can get us to the nth term. So it doesn't matter if n is equal to 0, 1, 2, 3, or any of these non-negative integers, this formula works. Now, let's take the sum of such an arithmetic sequence. I'm going to denote the sum by capital S sub n. So we want the sum of n terms in an arithmetic sequence. And we're starting from 0, and we're going up to n. So I'm going to use summation notation over here. I'm going to write capital sigma, and this sum is going to be going from 0 to n. And I have to introduce another index. This index I'm using is I. So I is just a dummy index that I'm using for this summation notation. And this over here is the capital Greek letter sigma. So that's just summation notation with a dummy index I. I'm choosing I because we don't want to confuse this index with the index n. N tells us how many terms there are in the sequence. So let's have a look at what we're going to get. Let's write this out explicitly. So the 0th term is going to be a sub 0. And we're starting from 0. So we're not saying this is the first term, we're saying this is the initial term. It's the term that corresponds to I equals 0. Now let's go to the term that corresponds to I equals 1. All we have to do is add one of those d's, one of those common differences. So that's going to give us a0 plus d. And let's add the next term. The next term is a0 plus 2d. So that's what we have over here. These are the first 3 terms, 0, 1, and 2. So this is I equals to 0, I equals to 1, and I equals to 2. And I'm going to leave some dots for the terms in the middle. I'm just going to skip over to the final 3 terms. And the final 3 terms are going to look very similar to this. There's actually going to be a slight symmetry. And this symmetry only emerges if you start counting from 0. That symmetry disappears if you start counting from 1. And that is my reasoning for choosing this convention of the index n. So let's have a look at the final 3 terms. The final 3 terms are going to look like this. We're going to have a0 plus n minus 2 copies of d. Then we're going to have a0 plus n minus 1 copies of d. And finally, the final term in the sequence is going to be the nth term in the sequence. And that's going to be a0 plus n copies of d. So you can see there's a d over here in all of these guys because they all have the same form as this general equation up here, this general formula for any term in the arithmetic sequence. And I want you to notice the symmetry between the 0th term and the nth term, the I equals 1 term and the I equals n minus 1 term, and these two terms here. You can actually pair up all of the terms in an arithmetic sequence. And that's what we're going to use to derive an expression for this sum. So this is equal to, what are we going to have? If we pair this guy and this guy together, that's going to give 2 times a0 plus nd. And it turns out that all of these pairs are going to give that exact same sum. So this 0th term plus I equals n, this I equals n term, these two terms are going to combine to give this, because we have 2 copies of a0 and then we have nd. So that's what we have over here. And what about this term and this term? Again, we have 2 copies of a0, this n minus 1 and this 1 copy of d over here. They're going to combine together and they're just going to give n times d. So we have 1 over here implicitly, and we also have n minus 1. So that just gives 1. What about these guys over here, these two pairs? So here we have 2, and here we have n minus 2. So 2 plus n minus 2, that again gives n. And we can keep on going until we get to the middle. Now at the middle, we're either going to have a pair of terms, or we're just going to have one term by itself. That depends on whether n is an even or an odd number. So if n is even or odd, we're either going to see a pair or just a single number in the middle. But regardless of whether this is even or odd, we're going to need n over 2 copies of this sum. So n over 2 copies, because there's going to be n over 2 times this sum occurring in this sum over here, the sum of an arithmetic sequence. So have a look at this expression over here. We can rearrange this slightly. So we can write this as n minus 2 times a sub 0 plus a sub 0 plus nd. And what is this in brackets over here? Well, that is just this term. So we have the first and the last term. We could have picked any of these pairs to put over here, but I specifically picked these two guys, because then I can choose to write this in a very suggestive form. We have n times a0 plus a sub n, all divided by 2. So we add the 0th term and the nth term, and we divide it by 2 and multiply by how many terms there are in the sequence. So this is the general formula in several different forms over here, for the general formula of the sum of an arithmetic sequence. Now, what would happen if you kept going, if you kept increasing n, in the limit as n goes to infinity? Well, you would not get a convergent result. This would diverge, because you're either adding or subtracting a common number. You're adding or subtracting this d, depending on whether d is positive or negative. And that is not going to give a finite result. So in general, the limit as n goes to infinity, that's going to diverge. But we're going to see a different sort of relationship for the geometric sequences. So let's have a look at geometric sequences. We can also do an analogous recursive definition over here. So a sub n plus 1, that's equal to a sub n times r. Here we have a common ratio. And over here we're multiplying. We're no longer adding. In an arithmetic sequence, we're adding, and over here we're multiplying. And I want you to see that addition actually encompasses subtraction as well. So subtraction is just adding negative numbers. You're just adding negative numbers over here. So if d is negative. And over here, if we're dividing, if we want to divide, we just have to multiply by a fraction. We have to multiply by the reciprocal of a number. And that's the same as dividing. So multiplication encompasses all of division, and addition encompasses all of subtraction. So this is the recursive formula. Let's write an analogous general formula. The analogous general formula is going to have the form a sub n equals a0 times r to the power of n. And again, I'm using this convention that n has to run from 0, 1, 2, 3, and so on. So it includes 0. We begin counting at 0. So a sub 0, that is the initial value, and then we're multiplying by that common ratio again and again and again, n times. That's why we're taking the power over here. We're using this exponent, and that's giving us a sub n. Now, let's find the sum of this sequence. So if we write s sub n over here, what are we going to get? I'll write this out explicitly. We have a sub 0 plus a sub 0 times r plus a sub 0 times r squared. And then I'll leave out all those terms in the middle. Those terms in the middle, analogous to the stuff we have written in blue at the top. So over here, we're going to have a0 r to the power of n minus 2, just like we had n minus 2 over here. But over here, we were multiplying. Over here, we're taking the power, right? Because this is the same as applying r n minus 2 times. And then we have a few more terms remaining. We have a0 r n minus 1. And finally, the final term is a0 r to the n. So we have n copies of r. We're multiplying r by r n times. So that's that initial number a sub 0. We're just multiplying by that common ratio n times. And the recursive relationship tells us that all of the neighboring terms in this sequence, they only differ by a factor of r. Up here, all the terms differed by a little common difference. So the difference was the thing that actually separated these guys. But here we have a multiplication. We have a common factor. And that's why we're using a different letter. We're using r. And r is supposed to denote ratio. It's a common ratio between any of these guys. If you divide this guy by this guy, so if you have a n plus 1 divided by an, you're going to get that common ratio. And that common ratio works for all of these neighboring terms. So if you take this guy, or any of the neighboring terms. Okay, so now we have the explicit form of this sum. That's what we're trying to evaluate. And I want you to notice that over here, implicitly, we have r to the power of 0. Just as up here, implicitly, we have 0 times d. We're adding 0 copies of d. That's this first, or this 0th term over here. And this guy also has 0 copies of r. That's why this convention of starting from 0 is actually easier because you're looking at a symmetry. There's a symmetry between these guys. Now, to find the general formula for the sum, what I'm going to do is I'm going to multiply the entire sum by r. What's going to happen to this term? We're going to have a 0 times r, and then over here, this is going to turn to r squared. This is going to turn to r cubed, and I'll write all these dots over here. In the middle, all of these terms in the middle are also going to get multiplied by a factor of r. Then over here, we're going to have a0 times r to the n minus 1, right? This n minus 2 is going to get multiplied by r, so we're going to have an extra factor of r, and that's going to turn that into n minus 1. Then we're going to have a0 times r to the n, that's from this term up here, right? N minus 1 times another r, that adds 1 to the exponent. And then finally, we're going to have a to the 0 times r to the n plus 1. Right? We're adding an extra factor up here, so we're multiplying by r one more time. That turns this n to an n plus 1. Now what I'm going to do, I'm going to use a very interesting trick. I'm going to take s sub n, and I'm going to subtract off r times s sub n. So I'm going to take this row, and then I'm going to subtract off this row. So what is that going to be equal to? Well, that's the same as 1 minus r times s sub n. And what is that going to be equal to based on this relationship that we have over here? Well, have a look at some pairs we can make. If we subtract off this bottom row from this row, this guy is going to cancel with this guy. This squared term is going to cancel with this square term. This cube term, there's another cube term inside these dots. And these guys are going to cancel. What about over here? This n minus 1 term, it can find another buddy, it can find a pair inside these dots over here. This n minus 2 term can also find another pair in there. So this n minus 1 can find another pair over here. So all of these guys are actually going to be finding pairs, except for this term over here and this term over here. All the other guys have pairs, and they're all going to cancel out except for these guys. And I'll write those guys there. So we have a sub 0 minus, remember we're subtracting, minus a sub 0 r to the n plus 1. And we can factor out that a sub 0. If we factor it out, we're going to have 1 minus r to the n plus 1. So how do we get this? The way we got it is we just canceled out all of the other terms. We used this trick of multiplying by r and then subtracting to cancel out all the terms except this initial term and this final term. But this final term has a minus sign. There's a minus sign over here. And we can factor out that a0 out of here. And now you can see that this is equivalent to this, so we can divide both sides by 1 minus r, and that's going to give the general formula. So the general formula for the sum, right, s sub n, is equal to a sub 0, that's that initial value, times 1 minus r to the n plus 1, all divided by 1 minus r. So that is the general formula. for the sum of a finite number of terms. But what happens if we take s infinity, right? Let's have a look at what happens when we have s infinity. So if n goes to infinity, we take the limit, what we're going to do is we're going to say the limit as n goes to infinity of s sub n. So in the index over here, I'm writing infinity. That's the limiting case. What happens if we have an infinite number of terms? Well, that's actually going to be equal to a0 divided by 1 minus r. Only if the absolute value of r is less than 1. If it's equal to 1, it's not going to work. If it's greater than 1, it's not going to work. It's going to diverge. The only way you're going to get this to converge is if the absolute value of r is less than 1. And the reason I'm putting absolute value over here is because this r does not have to be positive. Just like d does not have to be positive. It can be a negative value. You can have a negative value whose absolute value is less than 1. This could be a half, it could be minus a half, and you will get convergence. So this is the limiting case. And how do we get to this guy over here? Well, if you take the limit as n gets really, really, really big, and r satisfies this condition over here, what's going to happen to this term? N does not appear over here, n does not appear in the denominator, it only appears over here. If you have a really, really big number, and you're using that number to exponentiate r, and r has a value whose absolute magnitude is less than 1, this is going to go to 0. So this is going to disappear as n gets really, really big. This is going to get really, really small as n gets really, really big. And so this term, this bit over here, disappears, and you're just left with the initial term divided by 1 minus r. So the most important little trick that we used to get this geometric sequence formula is this little trick over here. It's a sneaky little trick. We take the sum, we write it out explicitly, we multiply by the ratio, and then we subtract. We subtract this from this. So Sn minus Rsn. And from that, we can pair these guys together. We can pair this guy with this guy, the squared with the squared, the cubed with another cube that lives inside these three dots. This guy over here gets paired with this guy. We have n minus 1, n minus 1. And this n minus 2 can find another buddy. It can find a pair down here. So it's not explicitly written, but it exists in this middle bit over here with the three dots. And finally, this n term and this n term also can be paired up together. And the only two terms that remain that don't get paired up and cancelled from the subtraction is this initial term and this final term. And over here I have n plus 1 copies, right? n plus 1 copies of that common ratio. And that is what gets turned into this formula. And we've taken the limit, and we know it only converges if the absolute value of that common ratio is less than 1. Think about what would happen if it was equal to 1. If you had this equal to 1, you'd have 1 to the power of n plus 1. So this would remain 1, and you'd have 1 minus 1. And over here, you'd have 1 minus 1. So you'd be in trouble, because setting r equal to 1 would give you a singularity over here. You'd have 1 minus 1. And that's dividing by 0. And dividing by 0 is very problematic. There's no consistent way of defining that operation, dividing by 0. So that is why we don't have a less than or equal to sign over here. It is strictly less than. And it's very clear that if this is bigger than 1, this is going to blow up as n gets really large. This, you're raising a number that's larger than 1 to a non-zero power. You're adding more and more and more copies of that same thing. That's going to grow. It's going to grow and grow and grow, and that's going to diverge. So you won't be able to get a finite value for the sum. But if this condition is satisfied, and only if that condition is satisfied, you can actually get a convergent result. You can add an infinite number of terms in this geometric sequence. You can add those guys together, and you will actually get a meaningful answer. And that appears very frequently in physics. So using this formula, this case where n goes all the way up to infinity, this limiting formula, that is very useful in physics. There's a lot of physics applications, which we will see in the quantum mechanics playlist. So over here we have arithmetic sequences, and over here we have geometric sequences. And note that these guys, if we kept going off onto infinity, if n goes to infinity, we take that limiting case, we're not going to get a convergent answer. It's going to diverge because you're adding or subtracting continuously. But over here, there is a chance of getting a convergent result. There is a chance of converging on a finite value, but only if this condition is satisfied. So that is a necessary condition there. Okay, I hope this video was helpful. You can find other videos in the quantum mechanics playlist where we're going to use mathematical concepts like this to solve physics problems. You can find those videos if you click over here.